Okay, good morning, everyone. I'm going to start this day with a sort of general overview of all observations related from the high-level perspective. So what I'd like to talk about in this lecture is we're going to cover the OOPS interfaces that are related to everything observations. What are those interfaces, why we chose or why they were chosen, and hopefully that will give you an idea of what some classes are if you look at the high-level algorithms code. We'll talk a little bit about using different observation operators for different observation types, about the data flow for the observer post-processor. So that's basically how do we compute h of x during the model run, and just a bit on configuring observations in the configuration files. A recap from yesterday. So we have the abstract layer with the generic applications that use the abstract interfaces that are defined in OOPS. And then we have implementations of those interfaces. And typically, everything model related is going to live in the repositories that provide model specific interfaces like FE3 or MPass or Unified Model, etc. And everything observation related could be shared, could be used by any of those model interfaces, and the implementations live in UFO, Unified Forward Operator, and YODA interface for observation data access. And later today, Ryan and Steve will talk more about the implementations, but for now I would like to focus on just what are those interfaces that are implemented in UFO and YODA. Okay, so there are a couple interfaces that I already covered yesterday, so we'll just review that. One of the things that if we look at sort of data assimilation problem from data assimilation perspective, from something that we could read or write in a paper, is you would always see something that we call OOPS observations. So that's a vector in the observation space. It could be observation values highlighted here, or it could be the result of observation operators. So if you compute h of x, the result of that is of type or class observations. So that's one of the interfaces that you would see in OOPS. Another interface that we talked about yesterday is the departures, and departures is in some sense similar to observations. It's also a vector in the same space, right, in the observation space. The difference is that for departures is a difference between the two observations, basically, or between two objects of class observations. So y minus hx is a departure. The ensemble perturbations in the op space is also a departure. And they are separated into different interfaces because we could do different things with them. So the operations that we could define on observations and on departures are different. So those are two different classes in OOPS. Let's cover a few classes that we didn't, or interfaces that we didn't cover yesterday. So another thing that you would always see if you're doing Gaussian data assimilation is you would see the observation error covariance. So the covariance for the observation errors. So that's another class in OOPS related to the observations. And you can sort of think of what are the operations that are would be defined on this covariances. So you could, if you look at the interface of this class, you would see that you can multiply a departure by a covariance, or you can do an inverse multiplication. Okay, another class is an observation operator. So that's an h. So hx, as h of x, as we already discussed, is of type observations. The result of this ops operator is observations. But an operator itself, something that computes, goes from x to y space, is called obs operator inside OOPS. And that class has methods that simulate observation from what we see in the model space. Another class that you would see is in OOPS, it's called the linear obs operator. And that's where the tangent, linear, and adjoint of the observation operator live. So there are two separate classes. The nonlinear obs operator is called obs operator, and then the TL and adjoint live in the linear obs operator class if you're an OOPS. And if you look at the implementations in UFO, they would typically be called obs operator name and then TLAD at the end, but they implement the same thing. Okay, so to sort of review, we've just covered some interfaces that are related to observations that we could think of just from looking at the data assimilation equations. So we have observations or departures, and I also call it obs vector here. We'll discuss in a little bit why I do this here. This is kind of observations related class. We have a couple of observation operator related classes, and we have the observation errors. Okay, so we could also look at what we might need for doing a simulation from the observation standpoint, looking at it at what I think of sort of observation processing perspective. I'm not an observation processing person, but that's how I think about it. So we need to somehow access the data. We need to be able to do input output with the observations. We don't just have observation values. We have a bunch of metadata that would likely be needed when we do observation operators, et cetera. So we need to have efficient I/O. We need to figure out how we do MPI distribution between different processors, et cetera. And so this sort of everything I/O distribution, storing metadata, etc., in memory is what is done in the class that's called ops space. So you can think of that as sort of a container that might have the data or would allow you to access the data and would take care of the input output. Another thing that comes to mind when we start thinking about real-world data assimilation is we need to do QC. So for quality control, we have another interface class that's called ops filters. It allows you typically to do more things. The interface is fairly generic, that it doesn't just constrain you to do only QC in it, but the most common use case for this ops filters is QC. So if you hear someone talking about JEDI and they're talking about filters, most likely they're talking about QC process, the QC filters. And another thing that's important is the bias correction. So there are three interface classes in OOPS that are related to the bias correction. They all start with obs AUX, obs aux, auxiliary. And then there's a control, increment, and covariance class. And in some sense, if you remember yesterday, we talked about we have state and increment in the model space, with state being like a forecast state or background, and then increment being a difference between two states. And in the observation space, we have observations, which is observation value, for example, something that's a vector in the observation space. And we have departures, which is a difference between the two observations. So it's kind of similar for this obs aux classes. So the control is something in this obs aux space, might be bias correction coefficients. And then increment is a difference between the two. And then there's a covariance, just like we have covariances in the model space and the ops space. And in OOPS, they're called auxiliary and not bias correction because, again, they're generic enough that theoretically they could be used for other purposes. But if you look at implementations of those classes in UFO, say, you would typically see ops bias. Okay, so we've now have more interface classes that are related to observations. So there's some that I call observation-related classes. That's the ops space, so that thing that allow us to do I/O and access metadata, etc. And there's ops vector or observations, so the vector in the observation space. And implementations of these classes live in this JEDI repository. So that's where you would see how they are implemented for the use in JEDI. Then we have observation operator, QC, and bias correction related classes. And again, interfaces will be in OOPS, but the implementations, and in this case, would be in the UFO repository, Unified Forward Operator. And then we have the observation error class, the ops error covariance. We currently only have one implementation for the observation error covariances. We can only use the diagonal covariances, but this can be extended. That's an interface that could be implemented in a different way, and we could add cross-channel correlations, etc. in the future. So for now, we only have diagonal covariances, and the diagonal covariances are easy enough to implement in a generic way. And so we actually didn't have to have an implementation in Yoder UFO for that. It's a class that just lives inside OOPS, and OOPS already provides you with the diagonal observation errors. Okay, so those are the main interfaces related to observations that come to mind if we just start thinking about the problem from DA or from the ops processing perspective. And hopefully they are clear now that it makes sense what they might be doing, what the methods on these interfaces would look like. Okay, so a note on using different observation operators. So when we implement observation operators in UFO, we do it in a way that there are multiple implementation of ops operators there, but one ops operator only processes one observation types. So you would see there's an ops operator for radiance for, say, CRTM. There's separately an ops operator for RTTOF, separately an ops operator that could be used, say, for radiosondes. And they're all kind of processed separately. If we want to simulate different observation types, then we're going to use multiple observation operators. And the way the code is organized is we have a one-to-one relation between ops space, which is, you can think of that as something that's associated with one observation file, and an ops operator. So we can specify, okay, I'm going to read a file with the radiosonde observations, and here's an ops operator that I'm going to use for this. And I also want to read this file with MSUA radiances, and I want to run CRTM to emulate what the model thinks the radiances are. So the way this is handled is it's handled on OOPS level. So on OOPS level, there are classes that look like containers of multiple ops spaces. So there's an ops spaces class, and it basically has a vector array, if you wish, of multiple classes of ops space. So what it means is it says, okay, I'm gonna store, say, 3 observation types that were specified in the configuration file. So on OOPS level, there's a class that says, okay, if the first one is this one, the second one is this one, the third one is this one. And because it's just using an interface, it doesn't actually know which types there are, but it just knows that there are three ops spaces, but it's kind of hidden inside this ops spaces class. And the reason I wanted to talk about that is that kind of explains a difference between some observation-related classes. So we talked about observations and departures. And when we talked about observations and departures, we were kind of looking at data assimilation algorithms, right? The cost function or the Kalman filter equations. And so from data assimilation perspective, when I write those, I don't really care if I'm going to simulate 3 radiances or if I'm also going to simulate radiosondes. I just want to know, here's my whole vector of observations. And so observations class, that's an OOPS class that basically contains all the obs or all the HFXs for everything. So it's kind of like this ops spaces class. It's a container that contains parts for each observation type. And so when we write algorithms in OOPS, we operate in this observations and departures classes, and we don't need to know at that level how many different observation types came in the system. On the other hand, if we are working on a different part of the system, if we're implementing an observation operator, let's say, again, we don't need to know that there's going to be other observation types. We just want to fill in the part of this observations vector that corresponds with the current observation type. And so there is a class that's called obs vector, and an obs vector is basically part of observations or part of departures that corresponds to a single observation type. So if you write algorithm in OOPS, you don't know about obs vectors, you operate with observations and departures, the whole observation state vector. But if you write an observation operator, then you don't know anything about observations and departures. You just operate on this obs vector, which is part of the whole, is going to be part of the whole observation state. Okay, so in the from interface, OOPS interface perspective, it's actually the obs vector that has an interface. So obs vector is something that you will see in Yoda, but then inside OOPS, they are in generic way combined to create the whole observation vector. Okay, so going back to the schematic that we've looked at many times already. So we see that we have, let's say, FE3 implementation, and we have the observation operators implemented completely in UFO. And there's one arrow one connection that's missing from this slide, and it's that the model interface actually has to have some knowledge of this UFO repository, or where the forward operators live. And I'd like to talk about why and how the two are connected. Okay, so let's just talk about the observation operator. So, if we write the equations, observation operator takes us from the model space, from the state in the model space. So that's our OOPS class state, X. And we compute the result of the operator H, and that takes us to the observation space. And that's this obs vector class that we talked about. So that's a vector in the observation space. So let's say I were to design OOPS today, and I wanted to write an interface for the observation operator. What I would say, probably just looking at the equations, would be, okay, I'll have a class, I'll have a class that's called obs operator. The colon in this case specifies what's on the left is the class, what's on the right is the method. I'll call my method that's going to compute h of x, I'll call it simulate obs, because that's what we're doing. We're trying to simulate observation from what we see in the model world. And I'm going to pass it the state as an input parameter. So if you see const, just if you don't know C++, for the purpose of this talk, you can just think that when you see const with this ampersand, that's sort of a intent in parameter. So I'll take state on input, and then I'm going to have obs vector on the output. It doesn't have const, so that's sort of an intent in out parameter. So I'm going to have state on input and an obs vector at the output where I would put the h of x. So what's the problem with this approach and JEDI philosophy? State is something that is specific to the model implementation. So state for FV3 would be different from how state is implemented in MPAS or unified model, or WRF or any other model. They would have different grids. They would store things differently. But what it means for us, it means that as soon as state becomes model interface specific, that means that with our interface that I proposed on the previous slide, this ops operator also becomes model specific. If it has to take state on input and put something inside ops vector, that moment it becomes model specific, and then you can't repurpose the same observation operator or the same class to use it with a different model. So that doesn't align with our goal of trying to share observation operators between different partners and have this sort of pool of observation operators that can be used by different models. And the problem becomes quickly understandable, hopefully, with the slide. So if you want to have observation operators implemented in all model, then you have to just basically do it as many times. You'll have to implement all of them for every model. And that's too much work, too much unnecessary work. So what we do instead is we basically introduce an intermediate step in this process. So we don't go from state to ops vector directly. We kind of split the observation operator in two parts. The first part goes from state to a class that's called geovals. Geovals stands for geographic? No, I don't even remember what it stands for, but I think it's geographic values at locations or something like this. And you'll get used to this name after a while. So first step, we go from state to this intermediate class container that's called geovals. This step is called get values. And this is the part that kind of has to know about the model, because the state is model specific. So this get values operator has to be also model specific. But then after that, once we get geovals, which is a UFO class, we do the second part of the observation operator, and that part has to be model agnostic. Like at this point, at the point of the second step, we have to have enough information to complete our observation operator, but this information has to be not model specific, or enough not model specific to be able to share this part between different models. So what are the steps, get values and the ops operator? So the get values step, which is model aware and observation operator agnostic, is basically a horizontal interpolation. So the main model implementation dependent part is what grid your states are on. So get values is where the horizontal interpolation happens. So if we think, for example, about the radio sound observations, this part in get values, we're going to find locations of all of our radio sound observations, the lat-long locations, and we have a state, and we're going to interpolate the variables that we need to compute the observation operator to those lat-long locations. So if we need, if we only have temperature observations, then at this step, the 3D temperature field is going to be interpolated to the locations of observations horizontally. So you will end up, let's say we had 3 radiosonde observations and 3 different lat-long points. You will end up with 3 vertical profiles of temperature from the model. If you were doing, say, a radiative transfer model, then at this step, you would also end up with the vertical profiles, but of more variables at each location. So you would have a temperature and humidity and pressure profiles and some surface values, etc. But at this step, all the model needs to do is interpolate the variables, horizontally interpolate the variables that it's asked to interpolate. So it's a fairly, should be a fairly easy step for the models to implement. And this part has to be observation operator agnostic. So no matter which observation operator you're going to run after that interpolation, you still do the same. You just do interpolation at this step. And then this ops operator part, so notice slight change in what we now call observation operator. So if we think of just h of x, then this is going from state to the ops vector. So in terms of OOPS or UFO or JEDI, what you're doing is you're calling an ops operator of get values of x. And this part does horizontal interpolation, and this part does the rest. So what it gives us is this kind of interfaces. So instead of having one interface that I was proposing at the beginning, which would go from state as an input parameter directly to the ops vector, we now have sort of two steps. We go from state to this class geovals in the middle. That's where interpolation happens. And then we go from geovals, this is our input parameter now that we calculated here, to the h of x. So the benefit of this is from our messy previous picture where everybody had to implement every observation operator they needed. We have model interfaces implement this get value step to get to geovals once. And then we have observation operator that takes those geovals or interpolated vertical profiles and compute the observation operator, and that's also done once. And it's easily extendable. So if someone wants to add a new model, they write their interface to the model, they write their get values, and they immediately get access to all the observation operators that are already here. If someone writes a new observation operator, they write their observation operator from the geovals, and all the models immediately get access to that observation operator. And that's how it's organized in JEDI. Okay, so that's our list of OOPS interfaces related to observations. And the two new ones here are this geovals, so that's the intermediate step or class data structure between state and the ops vector. And then I haven't specifically talked about locations, but we need locations. You can think of that as just let long points for observations. We need to know those when to do the interpolation to go from state to the geovals. Okay, so with that in mind, let's talk a little bit about how we actually run h of x. We use what we call observer post-processor. So from yesterday's unique presentation, let's review what the post-processor is. We associate post-processors with the model run. And as model is run, the model run, if you look at the code, is pretty simple. There's a call to initialize, and then there's a loop that inside the loop calls the model step method and just asks the model to propagate state forward in time for the specified delta t. And then at the end, there's a finalize code. What post-processors could do is the post-processors also have sort of corresponding methods. There's initialize, a step that I call processing here, and the finalize. And they run after, so the model initializes run, and then we call all post-processors initialize, and you kind of, that's initialization that happens before the model is run. And then inside the model loop, as model is stepped through time, we do one step of the model and we call all the post-processors. Call another step of the model, call all the post-processors. So the observer, or what calculates h of x, is written as a post-processor. And in the initialize step, so before the model is run, it does some setup. So it sets up what variables we need from the model. So that's everything that the ops operators are going to need. For example, for the radiative transfer model, you'll want temperature, humidity, some surface variables, maybe clouds, et cetera, et cetera. For radiosondes, you would want temperature and wind components, pressure levels, something like this. So it sets up, that's the setup of what I'm going to ask from the model, what are the locations of observations, etc. And then it also allocates geovals for the whole assimilation window, so for the full window where you're going to run your model through. As it steps through the forecast, after each step, we fill in the geovals for this little observation window around the current step. So what it saves us from doing is we don't have to save full 4D state as we run through the model forecast. We can, at each step, just compute what we need for the observation operator, save that, and then discard the full 3D state and just move on to the next state. Once we run through the model, we have filled in those geovals for all observations in this window. So sort of in each of the steps inside the loop, we were filling in parts of observations that are relevant to current mini window. Once we run the model, we now have all the data to run our observation operators. So we run observation operators and we also run QC filters. And I call them here prior and posterior filter. And the only difference in those is what information they have access to. So for the posterior filters, you can think, for example, of the background check, which you have to run after you run the HFX. But there may be filters that you want to run before you run HFX, and those are called prior. So that's how HFX works. And the last slide, just to kind of, get closer to the next lecture that Steve is going to give on configurations. Just a brief overview of what you would see in the YAML configuration file related to the observations. So the blue and the orange sections are basically two sections inside observations. So they would correspond to two observation types. First one could be radiances, second one could be radiosondes, or it could be two different kinds of radiances. There's a couple of sections that are required. So you always have to specify ops space. And that's typically which file to read ops from, etc. Ops operator, which observation operator you want to run on this ops space. Ops filters is for QC. Ops error you need if you're doing data assimilation. So that's what is your observation errors look like. And then you could have information on the ops bias. And then you would have another section that would have different information for the next observation type. And that's all I have for today. We can